shot. If it doesn't work, I'll have to slum it and use the whiteboard. All right, so limit as h approaches 0 of e to the x plus h minus e to the x all over h. All right, that's just subbing into the difference quotient. The first component is the f of x plus h part, then our f of x all over h. It's what we do from here that makes all the difference. The rule, the rule is right below, so we technically could just memorize that, but where's the fun in that? Slash, you've seen those multiple choice questions on tests. You know that they ask more about theory than actual procedural stuff. All right, so this part can be broken up. We'd write that as e to the x times e to the h minus the e to the x all over h. All right, so that's keep the base, add the exponents, but in reverse. All right, anytime you have a sum in exponents, that's a legal maneuver. You break it up into a product. All right. The reason why we do that, or we would think to do that, is because now I have a common factor of e to the x. It doesn't have an h in it, so it can come out of the limit completely. Okay, so this is where we kind of get to a little bit of an impasse. It's not really an impasse. It's just there is a reason why this limit is equal to 1. There's actually two reasons why. One's a graphical reason. Another is something called L'Hopital's rule. And we actually will get to that a little bit further down the line because we have to learn about implicit differentiation first. But I don't want to make it like a mini lesson here because what's going to happen is it's going to oversimplify a topic that deserves a little bit more attention. And so basically at this point what we're going to do is assume that that's a rule, kind of like the limit as x approaches 0 of sine x over x is equal to 1. This will be by rule equal to 1. All right, so the triple equal sign is equal by definition, at least for now. All right, later on, I think maybe a week and a half, 2 weeks, we'll prove why that is the case. And you can determine it visually. Right? If you put this equation, or if you put it in as an equation, y equals e to the x minus 1 over x in your calculator, and just visually determine the limit as x approaches 0, you'll see that it's going to 1. Right? But in terms of an analytic proof, we'll have to wait. All right, but the result would be that f prime of x, the derivative of e to the x is actually e to the x. So a function that has its own derivative. Pretty cool. So at any point along the function e to the x, its slope would be modeled by e to the x. They're just interesting to kind of wrap your brain around. But if you actually know the origin story behind the number e, you'd think it would probably make perfect sense.
It's actually a letter.
Thank you. So,
Wait, what?
in case anybody didn't get that joke. It's a letter in its appearance, but it's a number in the fact that it's a number.
The rule part doesn't have to have the coefficient on it to be the rule, right? Like the bracketed part doesn't have to have e to the x multiplied.
Correct. Yeah, it's just black.
Yeah.
Yeah. All right. So, yeah, that number 2.718 actually is derived from the concept of a slope. All right, we can talk about that down the line, but at this point it's not overly relevant, I suppose. So we get to this idea, the rule here. This is the chain rule variation of this, which is to say that if you have, and so they use u's instead of other functions, but if I had something like d dx, well, I'll write the general chain rule. The derivative of f of g of x would be f prime of g of x times g prime of x. All right. So how does that connect here? If we assume that u is some function of x, then it'll play out the same way. Bless you. So let me zoom in again. All right. So if I'm basically doing the same thing but with an e to the u, what I'd be looking for is the derivative of e to the u, all right, multiplied by the derivative of the u itself. All right. So all right, but we know that the derivative of exponential e would be the exponential e itself. And so, and the alternative notation for this would be du dx. All right, so it's following the same model. It's basically us saying that I'm going to take the derivative of the function, but the derivative of e to the x is e to the x, so we'll keep it as is initially, and then multiply by the derivative of the exponent. So it's following the same form. It actually is a chain rule in action. And you'll see that pretty much every rule that we have from here on out is going to have a chain rule component to it. All right? Where it's, oh, now it's super tiny. Where you're going to have the general rule as it applies to a parent function, but then a general rule as it applies to a function within a function. All right, so it may not just be e to the x, it may be e to the x squared or something like that, in which case you have that additional layer. But things like the constant multiple rule are still in effect. So when I look at number one, oh, that's poor quality F. The derivative of that would be the constant multiple multiplied by the derivative of the parent function. But we just discovered that the derivative of e to the x is e to the x. Sometimes it's a combo problem where you have a sum or a difference within the function. All right. So if that's the case, you might incorporate more than one technique. So f prime of x would be looking at the derivative of e to the x, which is e to the x. And then the derivative of negative 3x to the 6th power, which would be what? Negative 18x to the 5th. All right, so sometimes they're not that bad. Sometimes you incorporate quotient rule, product rule, some chain rule, more possibly chain rule, but maybe some other techniques. All right, so all those other rules, they never go away, but they're not always as intricate as they might have been in the quotient rule practice that we worked on in class, or the product rule practice, because those are designed to kind of extend you. Here, sort of introduce you to the skill. So personally, I always write my denominator squared first because I'm afraid I'll forget it. So low d high. So low d high, derivative of the high term would be e to the x. Yeah. Minus high, so e to the x. d low, which would be a 1. All right. Now, if I had to do something like find the second derivative, any higher order derivative, it serves a purpose to simplify that potentially, but without being told to or without having a reason to, I feel no need to. All right. Number 4, product rule. Still working with basic exponential e. First function times the derivative of the second function, e to the x has a derivative of e to the x, plus the second function times the derivative of the first. Derivative of the first function is just 3x squared. All right. So number 5 is the first problem where it starts getting a little, I wouldn't even say hard, I'll just say different. Yeah, a little spicier. Yeah, probably, I mean, it's like, it's chili, but it's like mild chili, all right? So, like, yeah, I mean, it's not, you wouldn't even consider it spicy. You know, like it just has it has the natural spices associated with a mild chili, but you're not thinking, "Ooh, this is spicy." You know, I have chili for lunch today, so I'm very excited. Homemade, you know. I mean, it's very easy to make. Just need the seasoning. As much ground turkey as you want, because I mean it's ground turkey, so you can't go wrong with that. A can of crushed tomatoes. Half a jar. You can go beans or without beans, depending on preference. I like the beans. They add a little extra oomph. Half a jar of your favorite Italian sauce, whatever it is, marinara. I'm a tomato basil kind of guy. So the Rayo's tomato basil, I feel it lends itself very well to the chili because it has the chunks of tomato in it. So, yeah. I can do that. Yep, the scooped Tostitos. Yeah, that's where it's at. Yeah. I can make that happen. When is not a good time to eat chili? That is the question.
I always eat lunch now.
Yeah, 9:23. You see that? I see chili o'clock. The chili comes with
it's so hard.
Scoop Tostitos. I mean, folks are welcome to bring whatever sides they would like to bring. I will take care of the chili part. So anyway, and so that'll be the Friday before break. Listen, people have let me down before on this. Like, I come in with, 1 year it was the goulash, because people said that they wanted to try my goulash, so I brought goulash in to one student in class because everybody else was absent that day. I'm like, all right, cool. One student. The day before the holiday break, and I was like, but that's the thing, like, it wasn't a surprise. We had discussed this weeks in advance and over a period of several weeks. Like, all right, we're all going to be here, right? I'm not going to bring the goulash if you're not going to be here. And then I walked in, they weren't here. All right, so what do you want, mild or medium? I'm not going to go spicy. Medium? Little extra something? All right. All right. So we have a little chain rule action going on here. You can define your U and your Y if you want. It's up to you. I like, at this point, when you start incorporating more complicated functions, I like to go with the shortcut approach. But just so you know, I think it was yesterday in my regular calc class, I went through, like, slow and steady, the chain rule. And so it was the first time they were seeing it. And And so I took a very deliberate approach to it. I walked through step by step how to do it the long way, and then I connected it to the shortcut approach. I know in this class it was more discovery, and then, by the way, here's the rule. Cool, now you know it, let's move on. So if you feel like you need another look at that, or maybe a more stretched out look at it, you can look at my regular calc videos. All right, so it's not anything terrible. If you do end up looking at it, it's not like, oh my God, I had to look at the regular calc videos. I'm ashamed of myself. It's not like that. Sometimes you just need a longer view or something. All right. So the shortcut, though, we're looking at something being raised to the third power. The derivative of something to the third power would be 3 times that something to the second power. That something being e to the x minus 4. Chain rule tells us to multiply by the derivative of the something. What is the derivative of e to the x minus 4? E to the x. That was nice. I mean, it was. It looked like it would be more complicated than maybe the quotient rule, but I thought it was maybe easier, maybe on par. Number 6, we have e to the x to the third. You might look at that as being something very similar to number 5, because it basically is the same thing, just without the minus 4. But when you're dealing with a monomial raised to a power, one thing you could always do is multiply those powers right off the bat. Make your life slightly easier. All right. Now, we have a model that tells us if I have e to the u, the derivative is going to be e to the u times u prime, or du dx. We'll go back and forth with the different types of notation. All right, so this is my u. So if I want a derivative here, f prime of x would basically be telling me to rewrite my original expression, e to the 3x, but then multiply by the derivative of whatever the exponent is, in this case, a 3. All right. In the end, it ended up being the same amount of work, most likely, I think, because you would have done the something to the third, 3 times the something squared times the derivative of the something, which would be e to the x. I mean, we get a slightly different looking answer. I mean, slightly, very different looking answer, but they're both equivalent, so it all comes out in a wash. All right. This follows the same model, e to the u times u prime. So e to the 3x minus 2 times 3. Number 8's pretty much the same idea. So, once you get a sense of the structure of your derivative, there's a lot of these that you can crank out pretty quickly. All right, so this is my u. We're looking at e to the x to the 6th times the derivative of my u, which would be 6x to the 5th. All right, and then we get to number 9, which, like all the other questions, has an e in it. So what do you say about the derivative here? Well, yeah, just tell me what it is. Tell me what the derivative would be. 7ex to the 7e minus 1. Very good.
Is that it?
That's the derivative, yeah? Yeah, it's a trick question. Yeah, it's not an exponential function. It's a power function, right? Because the base is the variable and the exponent is a number, right? 7 times e. So, power function, power rule. When you're dealing with an exponential function, you would have a base that's numerical and a power that's variable, so it's the reverse.
I would just took the 7e as a constant and take the 7e minus 1 as like in parentheses down. And
Yeah.
take a minus 1 out of all of that.
Yeah. Well, the only thing that'll end up ever being nice in higher order derivatives would be that the exponent is just going to become 7e minus 2, minus 3, minus 4, minus 5. But the coefficients are going to get more and more horrific. Yeah. So, yeah. Pretty nasty.